Building on SMA's portfolio of central inverters, we're also able to offer our customers a higher level of value in an integrated solution for medium voltage interconnect applications. These solutions can be deployed in 600 volt arrays or 1000 volt arrays and can be deployed in a number of different power breaks, from a 1 megawatt block all the way up to a 2 megawatt block, for instance. So the power breaks are determinant on the power of the inverters. So we typically have 2 inverters in a station feeding into a medium voltage transformer, which feeds into the point of interconnection. The benefit of a medium voltage solution to our customers is really a number of things. This includes decreased field integration costs, decreased quality excursions that could result from just the repetitive connection in the field and outside of a factory environment. By integrating in a factory environment, we're able to offer our customers an accelerated path to power generation. Instead of doing everything serially in the field in a makeshift assembly line type of environment, we actually take those activities, put them in parallel inside of a factory under tight quality controls, and accelerate your time to actually flipping the switch. This, of course, improves your ROI because you're getting paid for the power sooner. What is actually accomplished by a medium voltage solution? Well, the end-to-end processes encompassed by this turnkey deliverable include the inversion, well, DC collection, right, maybe DC disconnection, the inversion, and the step up to the interconnection voltage. And of course, all the control that goes along with that. So in terms of, say, standard equipment versus optional equipment, the standard deliverable would include the skid itself, and that's a steel structure. And to give you a feel for scale, it's roughly 12 foot wide by 30 foot long. The steel structure then has dropped on it the DC disconnects, the inverters, the control power and station power transformers, and the medium voltage transformer and switchgear. So all of this is factory assembled, delivered turnkey to your site. You can put it on piers, you could put it on a vault. That's really up to you. It's a very flexible solution. Now, in addition to the open skid solution, we're also offering a shade structure that drops onto the same exact skid. So it's not a start from scratch type of assembly process here. It's very modular. And in addition to the shade structure, a fully enclosed station. Fully enclosed station is not really necessary with our outdoor inverters. However, some folks would like to provide a structure for their maintenance personnel to work in, for instance. It's maybe just a little more convenient solution out in the field. In addition to the basics, there's a number of different options that you can configure. These are pretty highly configurable and, if desired, pretty highly customizable. The configurable options include the interconnection voltage, of course. We have many utilities in North America, each with their own distribution voltages, and we're able to provide the medium voltage transformer to tie into any of those voltages. The DC disconnecting means, which could be an integrated SMA disconnect right on the skid, or it could be an integrated circuit breaker panel board with zone monitoring CTs, all tied into your SCADA system. The switch configuration of the medium voltage transformer is also configurable. You could have a simple on-off radial type switch, or more commonly found, it would be a loop collection system. So we were able to offer T-blade, V-blade, or say a 3-switch combination. And this is an oil-immersed load break switch that would take the place of, say, a standalone piece of SF6 switchgear. And finally, the control power architecture on the station is configurable to include different power sizes of the transformer. You could include an additional transformer for feeding tracker motors, for instance, and of course communication media and power for SCADA systems. So in conclusion, the medium voltage solutions from SMA can provide you with a turnkey, high quality, high efficiency solution for large scale PV plants where it's very important to your ROI to deploy the solution and turn power on as fast as you can.
Today we're going to talk about integrating renewable energy into the grid in a reliable fashion. And specifically we're going to talk about the inverter functions that help integrate a large amount of solar into the grid, into the utility network. And we hear a lot about concerns from utilities about integrating those distributed PV systems and large-scale PV plants into their networks without certain features that are important to these utilities. For example, it's well known in the utility industry that inadequate characteristics of PV, for example, is you cannot dispatch it, it doesn't regulate the voltage, it's non-frequency responsive, it operates at unity power factor, it has variability with the ramps, and also, most importantly, it trips during voltage fluctuation, and they cannot do good stability model analysis on these particular plants. The utility would like to see some required characteristics that are used to in operating a conventional power plant, and that includes features such as the ability to dispatch, the voltage regulation, the frequency response, the power factor control, the write-through, and also the stability models to be able to analyze those plants in a reliable fashion. So currently, the PV market is regulated by IEEE 1547 and UL 1741, but this business is being transformed from what we used to call PV business into becoming now an energy business. And PV power plants now are contributing and becoming generation assets to utilities and conventional power producers. So utilities, ISOs, and reliability coordinator, unfortunately, are still applying the conventional large generation interconnection applications to PV power plants, and that's because of the lack of information and lack of standards for the PV interconnection. So at SMA, we have developed certain grid integrated features that are summarized on the slide, and basically talks about the ability to basically dispatch the power of an inverter at different power rating levels. Also, our inverters are equipped with over-frequency automatic response, and we'll talk a little bit more details about this feature in the next few slides. And we also are able to supply reactive power and operate the inverter in a power factor control mode, in addition to complying with FERC Order 661-A for voltage write-through. And because of our German requirements, we are also able to supply reactive current during fault write-through, something that's not required in North America, but it's a nice feature in helping recovery from voltage dips. The beauty of this is that all that I just talked about is under utility control, and that's what utilities like. They like to be able to control these plants and basically dispatch those units, whether you're dispatching megawatts, you're dispatching megavar, or you're setting the voltage requirements on the grid. So the beauty of it is that SMA also is equipped with the appropriate controllers to facilitate this particular task in integrating it not only to the grid, but to the utility control center. Let's talk about the active power limitation. Through our technology, you are able to dispatch the inverter at various power levels, usually 100% of power, 60% of power, 30% of power, or a standby 0%. That would be basically the default. But one can set 16 different settings to be able to change the power. And usually you try to do this to avoid sometimes grid congestion. A perfect example is the ERCOT market. It's understood there's some congestion sometimes, especially because of the wind that exists on the west side of the state. And ERCOT likes to have control over any sizable power plants in its market system and be able to dispatch that at different power levels. You're also able to control the ramp of the inverter versus the up ramp versus the down ramp. And it's configurable between 20 seconds and basically 60 minutes. The more important frequency that's also a requirement, like I mentioned in ERCOT market and other reliability coordination regions, is the automatic over-frequency response. Our inverters are equipped with the functionality similar to a conventional power plant, where if the frequency goes higher than a given threshold, in this case, maybe 60.5 hertz or 60.4 hertz or 60.2 hertz, whatever settings the utility requires, you can set a percentage droop for every increase in the 0.1 hertz on the frequency. The inverter automatically sheds power from its capability. So an over-frequency response is very important because when you have power surplus, if you have grid instabilities, or if you have any kind of grid failures, that comes into play. One of the most important features we're running into these days with the interconnection is reactive power compensation at the point of interconnection, and also the ability to supply VARs from within the inverter instead of the client buying, for example, capacitors or static VAR compensators or dynamic VAR compensation. So SMA inverters are equipped with the capability to provide VARs. We have various modes of operation. We have what we call a fixed mode, which means that the utility runs a study and it determines at the point of interconnection that the requirement to have a fixed power factor of, for example, 0.95 or 0.98 or 0.97 lagging or leading, which means that the inverter has to supply that power, reactive power, at the point of interconnection. The second option is basically to be able to provide dynamically, remotely controlled by the utility, a power factor requirement at the point of interconnection, and they usually give you a range, 0.95 lagging to 0.95 leading, or 0.9 lagging to 0.9 leading, etc. And that could change during the day depending on loads and voltages, etc. So that's also another capability that SMA inverters support. Third, you are able to also follow a grid voltage, and the power, reactive power automatically follows the grid voltage according to a predefined schedule. A lot of utilities have voltage schedules on certain buses, and we are able to load those schedules into the inverter firmware and automatically adjust the power factor. The point I'm trying to make is that our inverters are fully rated to 0.9 lag lead designed, and that's an important feature when it comes to basically minimizing the cost of the PV system. Now, what do we mean by point of interconnection? This is an example where the point of interconnection is at the 115 kV bus, and basically what we're showing here is a PV power plant that has a medium voltage step-up transformers to 34.5 kV, and then step it up to what we call 115 or transmission level. So the point of interconnection that the utility cares about is basically at the 115 point common coupling, at the common point of coupling. So why is that important? That's because if the utility requires a 0.95 lead power factor at the point of interconnection on a 100 megawatt plant, for example, there's a lot of VAR compensation that needs to come into play. There are, what we call GSU losses. There is the step-up transformer losses from medium voltage to high voltage. There's the grid charging. There's losses in the cables, etc. So this is a simple example. It's not meant to be a true representation of a power plant, because that usually requires studies by consultants or specialty firms that can do these plant studies. But just for illustration purpose, if I'm required to provide 100 megawatt as a PPA, for example, at the point of interconnection, with the 0.95 lead power factor, this can lead to a 0.986 power factor requirement at the inverter level. In this particular example, the inverter is supposed to suck out of the system 70 megawatt to comply with that requirement. Similarly, if I'm using a capacitive example, a 100 megawatt 0.95 lag power factor, that means I have to provide 33 megawatt of reactive power at the point of interconnection. If I work through the math, then I'm supposed to be providing 0.9 lag power factor at the inverter level, which in this particular example translates into 49 megawatt of reactive power from the plant. Now, of course, there are options that you can run this with a unity power factor and buy what we call DVARs or STATCOMs or add capacitors, but that also increases the cost of the system. The VARs from the inverter come at no additional cost to the owner or the developer. All right, so in order to facilitate the understanding to the utility that are normally used to rating the facility in MVA versus megawatts or kilowatts, SMA started also rating its inverter in kVA. So in this particular example, the relationship of apparent power, reactive power, and active power is shown in what we call Pythagorean theorem, and that's just trigonometry, in which case the apparent power, which is normally referred to as S, is equal to the square root of active power P squared plus reactive power Q squared. So for example, the SC800CP, which is rated 800 kilowatt, is also rated 880 kVA for temperatures of less than or equal to 25 degrees Celsius. What that means to the developer and the utility that are used to facility rating in kVA is that this inverter is capable of 800 kilowatt, but also it can provide a range of 360 kilovar, lagging or leading plus or minus 360 kilovar for that particular inverter type. Another important feature is the low voltage write-through requirement from FERC Order 661-A that was imposed due to the high penetration in the past. And now we're seeing more requirements coming also on PV. What happens here is basically the voltage dips to zero on the high voltage side of the high voltage transformer. In other words, the high voltage side of the grid dips all the way sometimes to zero. And the power plant is not supposed to disconnect, because if you do, then you are creating what we call a double contingency effect, a loss of a branch and a loss of a generation, which is an ERC violation standard, by the way. So our inverters are designed with the feature where you're able to ride through these voltage dips until the fault is cleared. And what we call the fault cleaning period time is usually 9 or 10 cycles. On a 60 hertz system, that usually translates into 150 milliseconds or 160 milliseconds. So in that range, the inverter can ride through these disturbances all the way to zero. And then as the voltage recovers, then the inverter starts recovering with it eventually until it stops pumping more power into the grid. But during the ride-through period, the inverter is not actually producing any power. It's just sitting in a listen mode, standby, monitoring the voltage until the voltage recovery occurs, and then it gets back online and then into resume normal operation. Now, if within 150 milliseconds, the voltage threshold or the voltage limit is still below a given threshold, then the power plant or the inverter, in this case, shall disconnect from the grid. And finally, to facilitate the planning, engineering studies of these dynamic stability behavior of the large power plants, we have developed dynamic stability models with our consultants for versions PSSE and PSLF, version 29, 30, 31, and 32 for PSSE, and versions 16 and 17 for the PSLF model. And those models are available upon request from SMA. Usually the developer will apply with the utility, and the utility will ask the developer through the planning department that they require, for example, PSSE version 31 or 32, or PSLF version 17, etc. So these models are available from SMA for the planning studies that utilities and ISOs and reliability coordinators require. And finally, I'm going to leave you with this slide where one of the most known figures for electricity is Thomas Edison. And I'll let you read his take back from 1931 on why we should use Mother Nature's most viable source of energy. And that would be, in his opinion, the sun. Thank you very much.